quickly by thanking all of you guys for coming out to an event like this. Those of us who are in Bremerton for the first time here for this all-hands meeting we have for LSST, the Large Synoptic Survey Telescope, have just been incredibly impressed with the interest in this community. For those of you who don't know, we've been holding public talks, real lectures, most of the other nights of this week over in the theater just down the road. And the first two were sold out, 102 auditorium. Most of us couldn't get in. And I've never seen that before in any scientific meeting. That kind of engagement with the community is just wonderful. So Bremerton's just a fantastic place. All right, so as Susan said, I am the director of the Large Synoptic Survey Telescope, which is the basis of the meeting that we're holding here. There are about 200 people coming to Bremerton this week. Most of us are people actively working on the project, but there are also, coming a little bit later, a number of scientists from the broad astronomy community who will be users of the telescope. So I thought I would use my time to tell you a little bit about what LSST is, but making it a little bit more personal, telling you how I got involved in it. So first, a little bit about myself. I'm a professor of physics at Stanford University in California, and I'm affiliated with the SLAC National Accelerator Laboratory, which is a large Department of Energy laboratory that's managed by Stanford. Before moving to Stanford in 2003, I was a professor at Columbia University in New York, and before that at the University of California at Berkeley. So the California, New York, California is because my wife likes California and I'm a New Yorker. She went out in the end, but that's another story. Anyway, LSST is a large facility for optical astronomy, which means it detects light in the wavelength range that our eyes can see, visible light. And it's the oldest field of astronomy, of course, because many of the earliest observations date back to Galileo when there were telescopes looking in that range. And even though I'm the director of the project, it turns out that field is new for me personally. Okay? I actually haven't worked on ground-based optical telescopes before. Prior to LSST, I was an X-ray astronomer, which means that I made studies of stars and galaxies in X-ray light, the same kind of light that's used in medical imaging. And X-ray light is a very high energy form of radiation, so it's only emitted by very hot gases and some of the most exotic regions of the universe. So the vicinities of black holes and exploding stars and hot gas, which is trapped in massive clusters of galaxies. Those are the kinds of things that happen. X-rays do not get through the atmosphere. So that field began in the mid-60s when we could launch rockets and eventually satellites above the atmosphere. And to do that field, I had to design and build satellite experiments that were in orbit around the Earth and made various measurements. One of the aspects of that field that I personally was heavily involved in is something called X-ray spectroscopy, which is the study of X-ray light as a function of wavelength or energy. And if you do a detailed analysis of that, you get a lot of information about physical conditions in these exotic environments. What are the temperatures, pressures? So we could do a lot of physics information, what's happening in these physics. So that's mostly where I spent most of my career. Actually, the culmination of that is I built an experiment on a European Space Agency, a satellite mission called Newton, which was launched in 1999 and is still flying now. So while I was engaged in that field, partly without my particular participation or notice, there was a revolution happening in the field of cosmology. Now, cosmology is the study of the structure and evolution of the universe as a whole. Okay, how did the universe begin? How is it structured? And how is it expanded over the course of cosmic time? The universe is some 13-something billion years old. It's been expanding since the beginning. And the details of how stars and galaxies and other structures form is the basis of astronomy. When I was doing my PhD research in the late 1970s, this field was really quite primitive. And in In fact, our understanding of basic questions in cosmology was really very minimal. In many respects, the field was sort of more akin to philosophy or even parts of religion than it was to hard science. Most of the theories were based entirely on speculation rather than hard measurements. So I did not find this an enticing field to enter. I liked actually measuring things and figuring out with some certainty what's going on. But then a revolution happened. This was in the late 1990s. It's actually, I think, one of the most significant events in human history, and it's received a certain amount of attention in the press, but not as much recognition in the general public as it deserves. And this was the discovery by two different teams in the late 1990s that the universe was not only expanding, but that its expansion was accelerating with time. That was an amazing discovery. Okay, very much contrary to expectations. It's like throwing a ball up in the air, and rather than watching it decelerate, actually seeing it speed up as it goes up, as if gravity were working in the opposite direction. Okay? It turns out that, and the implications of that are really very profound for physics. It sort of implies that the entire universe is filled with a kind of energy field that has negative pressure. And we call that energy field has been called dark energy. And we have absolutely no idea what it is, or how it connects to anything else we know in physics. But there's absolutely no question that it's correct. Okay, so it's really one of the greatest puzzles. I think it's one of the most significant scientific discoveries in my lifetime. Even though I had nothing to do with it. And what the most amazing thing about dark energy actually is not only that it exists, but that it solved a bunch of problems in cosmology. So part of my distaste for cosmology prior to the discovery of dark energy is that there were these pretty fundamental problems. For example, although we had some understanding of the structure of how galaxies were distributed, it didn't fit with the dynamics. Galaxies appeared to be moving too fast for the structure, and that was sort of a problem. But the biggest problem, and the one I like the best, is that the oldest stars in the universe were older than the universe. That's kind of hard to make consistent. And so it's hard to have a lot of confidence in a scientific discipline that has such a fundamental inconsistency to it. Well, the discovery of dark energy actually solved all those problems. It's kind of amazing. When you allow for the existence of dark energy, the universe is older than we thought, and it's in fact comfortably older than the older stars. And also these problems I talked about with the velocities and the galaxy distribution, all amazingly got solved. So we don't understand what dark energy is, but if it's there, it actually makes all kinds of things fit together. So this was too enticing to ignore. So although I had nothing to do with this, I decided, okay, I'm going to drop everything I'm doing, and I'm going to become an experimental cosmologist, because I personally want to figure out what the hell is dark energy, and how does it relate? So what does all this have to do with LSST? The LSST, as I mentioned, is the Large Synoptic Survey Telescope. It's a very unusual telescope, actually. There's nothing else like it now in the world, and there probably won't be anything else like it. It's really a world-unique facility. It's a very large federal project, $650 million to construct it. And that contribution is partly coming from the National Science Foundation and partly coming from the Department of Energy. The idea behind LSST is very simple. We build a big telescope with an extremely large camera. And we use that to just take pictures of the universe. Every single picture includes a lot of sky. We can do it very quickly. And then we step around and we can cover the entire southern hemisphere of sky every few nights. And we're going to do this continuously for 10 years. So over 10 years, we'll measure everything that moves in the sky. All the asteroids, comets, other things in the solar system. We'll also measure everything that changes in the sky, all the variable stars, exploding stars, and things like that. And if we take those 10 years worth of data and add them all together, we'll measure everything in the sky. We'll measure billions of galaxies. actually detects something like 20 billion galaxies. It's the first time in human history that we'll know of more objects in the universe than there are people on Earth. So everybody on Earth can own their own galaxy. Actually, we can give them a star as well. There's plenty to go around. And they can study those objects to their heart's content. 20 billion galaxies is kind of an amazing number. It's actually a few percent of all the galaxies in the observable universe. What does that mean? Observable universe isn't because we can only build a certain size telescope. It's because as you look further out in space, you're also looking further back in time. And eventually you get far enough back in time there weren't any galaxies. So the number of galaxies in the observable universe is actually a finite number. It's about 100 billion. And so we're actually going to catalog a pretty good fraction of everything there is to know about the universe, at least in terms of galaxies and things like that. It's a major human achievement, even if you don't do any science with it. Okay, so what does this have to do with dark energy? When you have such a large number of galaxies, you can start to do very subtle statistical measurements on how are they distributed and what are their connections with one another. And that turns out to give very constraining information on the expansion history of the universe. One of the most exciting ways to do this is via something called gravitational lensing. And this is because the light from a distant galaxy, as it makes its way to Earth, has to pass by other concentrations of matter. There's a gravitational field associated with other concentrations of matter, and that bends the light. So the light from distant galaxies doesn't make a straight line toward us, it makes a sort of circuitous path. And that leads to correlations and distortions of galaxies that are measured. It's a fantastic idea. It also turns out to be extremely hard. We're looking for very, very subtle effects. And in order to do that, you have to really understand the telescope and the camera and everything else you build. Because you want to ensure that what you're measuring is really something to do with the cosmos and not just some error in the way you built your instrumentation. So this is exactly the kind of problem that I personally love. One in which the details of what you're building is tied up with some intricate esoteric theory, which is tied up with some complicated data analysis. And so I decided I had to do this. So I left Columbia University, I moved to Stanford and SLAC, and I decided I was going to put together a team to build the 3 billion pixel camera for LSST. We have fantastic engineers and physicists at SLAC. Many of them come from particle physics, and Dominique will talk a little bit about that in one of his later talks. And we put together a fantastic team. We were able to get money from the Department of Energy to build this thing. We got money for the telescope from the National Science Foundation. And frankly, the hardest part of this job is dealing with those 2 federal agencies. Okay. I am now the director of the entire project. And the telescope is being built in Tucson. The camera is being built at Stanford. So I bought a house in Tucson. I fly back and forth every couple of days. My wife and dogs go to Tucson in the winter when it's pleasant, and they leave Tucson in the summer when it's not pleasant, and spend the time in the Bay Area, and that's been my life over the last few years. But let me just conclude by saying this is a very exciting project. I feel very lucky to be involved in that, and I really appreciate the interest from your community in coming out to hear us speak. Thanks very much.